that comes with it. Yeah, so we are also not immune to all these things. We are also having some or the other problem, but as they say, the show must go on. So ensemble techniques, that's the topic that we've been discussing. We'll pardon me, we'll be discussing about that. We've had some brief discussion about tree-based models, and whatever discussions we had on the tree-based models, it eventually kind of, we had great difficulty in stopping ourselves from not discussing about the ensemble technique, because that is the logical path forward. You are in tree-based models and you realize that there's so much of limitation, and therefore let's go to ensemble. So yeah, we'll move to ensemble techniques today. We will discuss about that, and we have Sharath and Barney as always there to do the heavy lifting. Okay, so first question just today, I'm going to direct the question to Barney, primarily because Barney has done some seminal work with reference to a lot of content creation in the space of for our participants and students, made things very simple, and a lot of work, a lot of research he has done in the space of ensemble techniques. So my question is to start with a very generic question, Barney. Flow path of an ensemble method. Can you just quickly guide us through, when I say ensemble, what all does it encompass?
Okay, sure. So thank you so much, Nitin, and welcome everyone, whoever is attending this session. We have offline received a lot of positive feedback saying that people are watching our videos offline, if not online, attending while the classes happen. Either way, as long as you're watching, as long as you feel that it's benefiting you, we will be extremely happy. Okay, so let me share my screen. And here is one of the beautiful visualizations which we have come up with to help people understand ensemble methods. And to answer the question of Nitin, when it comes to ensemble techniques, we have heterogeneous models, homogeneous models, tree-based models, and non-tree-based models. Also, we have generative models and non-generative models. Within non-generative models, we have voting and stacking. When it comes to generative models, we have bagging, random forest, boosting. Within boosting, you have ADA boost, extreme boosting, gradient boosting, extreme gradient boosting, light GBM, and cat boost. So these are, I would say, algorithms which belong to the family of ensemble techniques. Yeah. Over to you, Nitin.
Thank you, Barney. So yeah, I was honestly, I was asking that question in the perspective of that visualization that I had seen, and I wanted you to also share it with our participants. So yeah, I'll jump into some specifics now. Sharath, I'll come to you in just a moment. So what is generative and non-generative by definition? Is it, as the word suggests, generates and doesn't generate, or could you just as a layman, for a layman, explain what is generative and non-generative?
Yeah. So in generative model, your subsequent models will take some motivation or some information from the previous model. Hence, it's called as generative, right? Even for that case, bagging generates a lot of samples as well, right? So that is also called as generative. When it comes to non-generative, it's more or less like you take the underlying data and you split the data once, build the model once, job done. So you really don't have any dependency of previous models on the subsequent models, right? But there's a thin line over there, Nitin, to help people understand. Because when it comes to bagging, right, they are all standalone algorithms, but ultimately it is categorized as generative for some reason, right? Otherwise, the underlying rationale behind segregating in that way is that when your subsequent algorithms are dependent on previous algorithms, it's called as generative. Otherwise, it is non-generative. Yeah.
All right. So before we dive into some pointed or specific questions with reference to ensemble techniques, Sharath, I'd like you to quickly tell me why ensemble, when we already have enough algorithms, whole plethora of algorithms are available. So why ensemble? Your take on that?
Yeah, good evening, Nitin. Good evening, Barney. Good evening, everyone. Yes, Nitin. So I would basically bring up a very simple question. You can see my voice is a little different today. So I was sick. Now, when I was sick, I went to the doctor, and doctor said that, hey, you have COVID. Now, should I directly believe that person, doctor? He would be a very senior doctor, a very experienced doctor. But somewhere I know that I may not have COVID. I don't want to trust it. So what I would do, ideally, I go for a second opinion. Right? So same case, when you are trying to predict any value using any single algorithm, the probability of the predicted result going wrong is always there. Now, we generally speak about accuracies. So let me just try to share my screen and scribble something. Okay, so this is basically the mind map where you have all the algorithms detailed here. You might want to just go through this. You have classification models, then we have the shallow machine learning techniques, ensemble models, then regression models, right? So all these are documented here. You might want to just go through this. So whenever we talk about any algorithm, we generally say that the model is performing at XYZ accuracy. For example, if I talk about a classification model, we will say it's basically having a 95% accuracy. So when you use this machine learning algorithm and try to predict new data, let's say I have a single record, one record, and I'm trying to predict the result on this particular new record. The model's accuracy says 95%. But that also means that there's a 5% chance that this prediction might be wrong. How do I rely on such a model which cannot tell me that this particular prediction is correct? There's always a chance of going wrong. So hence what we do is we resort to the ensemble techniques which improve the reliability. So what we do is simple logic. I will take machine learning model 1, irrespective of the accuracy. So let's not get into the accuracy point. I will try and predict this result on the new data using machine learning model 1. I'll get some result. I'll take machine learning model 2, machine learning model 3, so on and so forth, depending on the computational capability, the time frames that we have, the complexity with respect to the data and all that. Various factors we will include, and we will try to choose multiple models, and we will try and predict the results on the same record using all these individual models. The point is, if machine learning model 1 says, hey, this is 1, let's say student's case, it's pass, or COVID's case. This model says the patient has COVID. But this model says patient does not have COVID, then obviously there is some issue with one of these prediction models. So I will take much more list of many such examples, many such algorithms, and I'll try to do the prediction on the same record, and I will choose majority. The idea is single model may go wrong, but multiple models on the same data, the chance of going wrong is less. So we can improve the reliability of the predictions that we are making when you choose ensemble models. This is one practical application or why we use machine learning models, right? So this is one of the primary reasons. Of course, there are other benefits that we get when you use ensemble techniques, like it can handle imbalanced data better. It can handle missing data better, so on and so forth. Many such advantages are there. And while you choose ensemble techniques, like Bernie has mentioned, we have different ways to try and ensemble these models. So that's the reason, Nathan.
All right. Thank you so much, Sharath, for that analogical answer with reference to using your illness to talk about it. Yeah, that's an interesting take on that. So, Barney, my question to you, specific to bagging. Let's start from the sequence. So we hear about this, bootstrap aggregating. So can you explain to me what is bagging, and specifically within bagging, what is that bootstrap aggregating? What does it mean? It seems to be kind of fancy words. So could you just throw some light?
Sure. Absolutely, Nathan. Okay. So bagging, if you look at the name, has B and agging, right? So this is called as bootstrap aggregating. B as in bootstrap and AGG as in aggregating, or ING as well. Here, once you have your data set, when you create training data sets randomly, and if you have, say, 1,000 observations in your underlying data, and if you're trying to take, say, 80% of data into your training, and if you're randomly doing that, say observation number 2 would be part of this. And when you try to sample the next observation, you'll have all the 1,000 observations once again back in your data set. It's not that 2 is removed. 2 also would be there once again. So that means, once again, when randomly the observations are chosen, 2 also has equal chance of once again getting selected. That's called as bootstrap sampling. Bootstrap sampling means sampling with replacement. So whatever observation you take, you once again replace it back into your data set, and then randomly pull the next set of observations. Yeah. So that's called as bootstrap sampling.
So,
or bagging.
Okay, so obviously bagging is not as good as a scenario where we are sampling without replacement. I mean, are we in agreement on that, or are there certain advantages of other advantages of bagging in spite of sampling with replacement?
Okay, sampling with replacement and sampling without replacement are two different techniques that one can try out and figure out which technique actually works well. But usually sampling with replacement or without replacement do not have too many implications on the final outcome. But bagging works based on bootstrap sampling, which is sampling with replacement. Even without replacement, it doesn't matter much because it's just one observation, and the chance, as in how the underlying data, number of observations increase, with or without replacement will not have huge implication on what kind of data you are going to have on training.
All right. Okay.
Yeah.
So, Sharath, next question I'm directing to you. So we've also discussed about the concept of processing. All right. So not mainly processing, but modeling. All right. So we discuss about certain models are sequentially processed, certain models are parallel processed. At a high level, we understand that sequential processing is slow, and therefore intuitively is considered to be better. Parallel processing is faster, but you may miss out certain things. Anything other than that you'd like to add with reference to the differences between sequential and parallel processed models?
Yes, Nitin. So I would probably rephrase whatever you have mentioned. When we talk about bagging, those are parallel models. And when we talk about boosting approach, that's basically a sequential approach. I generally try and use an analogy. This is probably something everybody can correlate to, especially graduates. When you're trying to write your final exams, we generally, as a group, try to study. And probably before the exam, a day or 2 days, we generally distribute the units. We say that, hey, friend one, you study chapter one, I will study chapter two, someone else studies chapter three. And basically what happens in the exam, the discussion that happens, right? So individually, everybody is studying individual chapters. And when the exam actually happens, the capacity, the performance basically comes as the group study. So it's like all the individual friends discuss about their individual chapters that they have prepared and then write the exam. This is the analogy of bagging, where you're trying to do parallel studies, but on subsamples of data. Right? So the chapters here are basically nothing but subsamples that I'm trying to draw the analogies. And each friend is like a machine learning model that we are talking about, a tree-based algorithm. Whereas boosting is a sequential approach. And you can, again, talk about that one student who's always doing best in the class. His IQ levels are good. He is probably sitting in the first bench, right? So these students basically try and learn the subject by reading everything by themselves. So what they do is they take the first chapter, try and understand all the concepts. They may not be able to understand everything, but what they do is they try to go to the next chapter after the first chapter is finished. Chapter 2 is basically being now studied. They will try to also understand what is the concept which they couldn't follow in chapter 1 when they are preparing for chapter 2. So that they try to redo the chapters. But eventually, the same student is trying to study the entire subject. So this requires time. Obviously, if you have 10 chapters, you have to sequentially go through. Whereas when we talk about parallel, each student is studying one chapter. So all of them can distribute the work and then study. So the duration definitely comes down in the parallel models, that is in the bagging approach. And in sequential approaches, duration is generally the concern. But thanks to the distributed frameworks that we have, the infrastructure capabilities that we have, extreme gradient boosting is an approach which can quicken, right, this entire process. It can fasten up the entire process of sequential learning as well. So, but again, you need to have multiple processors to get this thing done. So this is the major difference between bagging and boosting that I would want to make a point of.
All right, thank you so much. So Barney, a part of what Sharath has mentioned, my question relates to that, and it is with reference to boosting. So we have, you mentioned about I think 5 methods of boosting, and my understanding, or everybody's understanding generally, is that progressively from the first model to the second, it is better. So why do we have ADA boost if we can have gradient boosting? Why do we have gradient boosting when we can have extreme gradient boosting? I want you to kind of elaborate on the advantages of the lower order models. I mean, I'm talking about, let us say, ADA boost has these advantages which others don't. Something like that you could throw light on.
Sure, Nitin, absolutely. So it's something like after first standard, you go to second, after second, you go to third standard, right? So you progress. And same is the case with boosting algorithms also. The world started off with ADA boost way back in 1994, if I'm not mistaken. After that, there have been enhancements which people have done. But ADA boost was working on the concept of decision stump. What do you mean by decision stump? You just split the tree once. That's it. Okay, this is called as decision stump. And multiple such algorithms were built, right? And gradient boosting was an enhancement over ADA boost, wherein gradient boosting looks at the errors and it will consider the errors or residual values as the output variable. And then it will start building the model. That's how gradient boosting works. And while bagging and random forest have parallel processing capabilities, that means if you have quad core, and if you're saying that, number of estimators, that is number of algorithms that you want to run 100, for instance. So what will happen is you'll have core 1, core 2, core 1, core 2, core 3, and core 4. And in each of these in parallel, there'll be 4 estimators or 4 algorithms which are going to run in parallel. Such provision is available in bagging and random forest. However, within boosting, since the next algorithm that you build is dependent on the previous one, we cannot perform parallel processing when it comes to ADA boost and gradient boosting. That is when people have explored further, and then today as we stand, we have an amazing algorithm called extreme gradient boosting. Majority of the competitions which are won are won because people started using XGBoost or the deep learning neural network algorithm. So that's how the world has progressed. And then here, yes, we can certainly perform parallel processing by making use of the hardware, by making use of your hard disk also, by making use of your RAM, by making use of your cache memory, etc. People can achieve parallel processing. So that's how the world has progressed. And then extreme gradient boosting is very intense in the sense it takes a lot of time. So people thought, let's make it lightweight. Let us ensure that the processing happens faster, etc. That gave rise to light GBM and CAD boost. If I'm not mistaken, light GBM is from Microsoft and this is from Yandex. These two are 2 different companies which have come up with these set of algorithms. Yeah, over to you, Nitin.
Yeah. Thank you, Bernie, for that detailed explanation. So my next question again to you, Bernie, is with reference to the the non-generative models. Now, I'm going to ask you a question in relation to deep learning. So when we discuss about deep learning and then when we come up with a series or the multiple layers, we have the internet to help us. So suppose we are working with, let us say, an image processing application. So we have a standard thing. If for this particular size, use these layers and then you're good to go. You don't really need to reinvent the wheel as far as creating that stack is concerned. So on similar lines, is there any, yeah, absolutely. I didn't want to use that word.
Yeah.
So on similar lines, for stacking, you've worked with many projects. So on similar lines for stacking, do you feel that there is a standard stack that you use, a logistic regression and this generally gives a very good accuracy, or it is always we have to reinvent the wheel?
Okay. Not about reinventing the wheel, Nitin. Here we do not have any pre-trained models or transfer learning models. Pre-trained or transfer learning models are more towards deep learning.
So
however,
my question was basically choice of models. Do we have a standard set of these 5 or these 3 are always better than anybody else? In that perspective, I was asking, not in the perspective. Yeah.
Absolutely. So when it comes to stacking, it is always advisable to use algorithms which have the capability of capturing linear patterns as well as non-linear patterns. Because what if your underlying data follows a pattern like this? Then it has the linear pattern and also here it has a non-linear pattern. Given this is one thumb rule which people have to follow. And the second thumb rule is, if you are, say, choosing 6 different algorithms, we have to try and use all the algorithms, 6 algorithms, which have different underlying math operations. Ultimately, any machine learning algorithm works on math, some kind of a math. So we have to decide upon algorithms which have very different underlying, math equations, so that each algorithm captures patterns in a different manner. And then when we combine them, it makes a lot of sense. Yeah, that's my take, Nitin.
Okay. All right. Thank you. Thank you. So we have time for one final question. And yeah, my question once again, because you've been the person who has created all this amazing, content. With reference to, Bharat had mentioned about how the imbalance of data is kind of taken care when we are dealing with ensemble techniques. So can you explain a little bit about how or the various methods, or what does it do to take care of the imbalance or extreme imbalance if it is there? The
Sure.
ensemble.
Sure. So if you have imbalance in the data, and if you are going to, split the data only once and get the training data and then build a model on the training data, then chances are very high that if you have, say, for example, 90% as default in this underlying data set, and say another 10% is, 90% not default and 10% default. In this case, when you just split it once, chances are very high that your data might be biased in a sense. Maybe 90% of data is default, not default, another 10% is default. So you're training your data heavily on not default scenarios. But when you keep splitting it multiple times, and then when you actually build on all these different samples, then chances are bleak that each time when you take, your underlying data would have more of not default and less of default. Right. So this is how your ensemble techniques will counter the imbalance in the data set. And also when you perform certain other techniques such as stacking, etc., you couple that with cross-validation techniques, so that even if you have that imbalance in the data set, you ultimately end up building your model on every observation, more or less every observation. And you also end up testing your model on more or less every observation, right? So given this logic, ensemble techniques will help you avoid, building a model which is very biased. And that is how it handles the imbalance in the data. Yeah.
All right, Penny.
Yeah. Over to you, Nitin.
Yeah. So I think we just have a minute left. So I think we'll wrap it up a little early. So yeah, that's the thing about ensemble techniques, and it is ensemble, as the word mentions. I mean, I always I'm also a trainer, and you must be aware. So I always give the example of the movie wherein you have multi-star cast. It is a sure shot success, right? You have an ensemble cast. You have this actor, that actor. Everybody is there. You have multi-starers, and that is definitely a hit. So ensemble models are some. I think multi-starrer movies have derived inspiration from ensemble techniques, is what I feel. So most of the times, more often than not, it is ensemble methods that are able to really give great accuracies at the cost, of course, for not too much of explainability is provided. But if that is not a important criteria, definitely ensemble techniques is for you. So on that note, we'll wrap it up. Thank you, friends. And a quick request once again, our subscriber base should increase. You are the beacons of our company's success, each and every one of you, and you can spread the word. So please do subscribe. Please do pass on this information through WhatsApp groups, etc., amongst your peer group about the content that we are offering, so that more people can subscribe, more people can grow, and we will continue to do these sessions for your benefit. Thank you so much.
Thank you all so much, friends. Bye.